All right, welcome back to Differential Equations. We are going to talk about an easier way to view some things here. So in the previous chapter, right, we were talking a lot about Laplace Transforms, okay? And we get a problem, say something like this. We get a y double prime minus 5y prime plus 6y is equal to 0. Okay, sometimes it would be a function over here, sometimes it would be 0. These are a special type. These are called homogeneous. Okay, it's when the right-hand side equals 0. Okay, that's just a vocabulary that occasionally somebody will toss out at you. All right, let's see here. And what I'd like to do, because we have to do this for the Laplace transforms, we have to kind of know like what y0 and what y prime of 0 is, right? Because in order to take Laplace transforms of both sides, we're going to need these two. What I call these in this case. These aren't really that important. Okay, I mean, you need something here, but whatever that something is, as long as they're like, we'll deal with them. Okay, so we're going to use these as constants, kind of like we've been using constants before, which means I'm going to rename and reshuffle these to be whatever's convenient for me at the time when I need them. Okay, so first step, right, is take Laplace transforms of both sides. Okay, that'll work. And how do we do that, right? That's Laplace transform of y double prime, so that's s squared y prime minus s, I think this is just y of 0 minus y prime of 0 minus 5, right? And we have s, y of s minus y of 0. Yeah. And then plus 6, and then this is just y of s. And this whole thing was equal to the Laplace transform on the right-hand side, which is linear transformation, so 0. Okay, so what I'm going to do is normally I collect these pieces over here, right? Collect the y's's. So we're going to have s squared minus 5s plus 6, and these are all y of s, okay? And on the other side, right? This is going to be s, y prime, this was m, this was n, this is m. So we're going to say this is equal to s m, right, plus 5, right, oh wait, it's plus, it's minus 5 m, okay, plus n. Okay, minus times a minus, right, gives me a plus, and when I shove it to the next side, it's going to turn back to a minus, okay? And then we went through and we said, okay, this is s is equal to, this is s m plus n minus 5n, and this is all over s squared minus 5s plus 6, which we could factor. Of course we could factor it, we're going to have to do partial fractions, okay? If we couldn't factor it, we'd have to use complete the square, and we'd get a different answer, okay? And we're going to see that reflected in a little bit too, but that's what we would do if we couldn't factor it. Okay, so this is s m plus n minus 5m, and this is going to be what, s minus 2, s minus 3, I believe. Okay. And then we go ahead and we break these apart, right? We say, well, we have, say this is an a over an s minus 2 and a b over an s minus 3. And this equals sm plus n minus 5m. So it looks like we have an a, this is s minus 3, plus a b, s minus 2. Right? And we have an AS plus a BS is equal to MS, right, this one, S. And then we have a minus 3A minus 2B, right, and that was equal to N minus 5M. Okay. Two equations, two unknowns. There's as many ways, as you want to solve this. If I just multiply this by 3, right? We get 3a plus 3b is equal to 3m. On the bottom here, we've got negative 3a minus 2b is equal to negative 5m plus n. I'm just going to add them together. That's why I multiplied by 3 is because I just wanted positive b. I didn't want to deal with more negative things. So we have an n. 5 minus 3 is minus 2m. Okay. And then we can plug this back into any equation that we've had up until this point, right? So we could have a plus b is equal to m. So we have a plus n minus 2m is equal to m, right? And then solving for a, we'd have a is equal to 3m minus n. Okay. So we have our a and our b. I'm just going to leave them as a and b because, again, they're arbitrary constants, and whatever we picked for my n and my m, we could figure that out. Okay, but right now I'm just going to leave them as an a and a b. Actually, what I'm going to do, I'm not even going to call them that. I'm going to call this one C1 and this one C2, right? Constant 1, constant 2. Constant 1 for a, constant 2 for b. If you swap them, then you're just going to have constant 1, constant 2. Doesn't matter. Okay, but look at what we have here, right? We have y of s is equal to c1, 1 over s minus 2, plus c2, 1 over s minus 3. And when we take our inverse Laplace transform, right, we just get y of t, whole y, is equal to c1 e to the 2t plus c2 e to the 3t, right? And what I'm going to go off and claim here is that if you have a differential equation, okay, with constant coefficients, so if you have a differential equation with constant coefficients, okay, your answer is always going to look like a C1 e to something and a C2 e to a different something, okay? Now, there's little things that we could do in here. If you have a third order, clearly we're going to have more, right? We're going to see 3 e to some function of t, or yeah, e. So instead of going through the whole Laplace transform thing, okay, I'm going to suggest, well, maybe since we've done this, I don't know, several dozen times, maybe we could just guess what the answer is going to be and realize that if the differential equation just has constant coefficients, that we're going to be in this sort of a situation, okay? So what if I just said, well, we have y double prime minus 5y prime plus 6y is equal to 0, and I just say, well, why don't we just assume that y is going to be equal to e to some rt? Okay. Now, what we're going to have to do is we're going to say y prime is equal to r e to the rt, y double prime is equal to r squared e to the rt, and then what we're going to do is we're going to plug in and we're going to say, well, this is r squared e to the rt minus 5r e to the rt plus 6 e to the rt, because we set y is equal to this, right? So y prime was r e to the rt, y double prime r squared e to the rt equals 0. Okay. Now rt e to the rt is a constant, not a constant, but it's a recurring term, right? It's common to all of what we have here. So this is e to the rt, r squared minus 5r plus 6 is equal to 0. This piece here, this is never equal to 0. Okay. So all we're going to do, right, e to the rt, no matter what r is, it's never going to be 0. So we're just left with solving this. This is r minus 2, r minus 3 is equal to 0. So r is equal to 2 or r is equal to 3. So we're going to say that our y, not y1, just y, okay, is equal to our c1 e to the r, right? It's now 2, right? In one case it's 2, plus c2 e to the 3t. And that's what we're going to call our solution here. Okay, if that is how we're going to be solving, the first order, second order, third order differential equations like this. Okay, that are homogeneous with constant coefficients. So we don't have any x's in here. Okay, that's next. What's it? Not next, but it's the next module. And the right-hand side is 0. Now, it doesn't have to be, and we're going to learn, like, the next section, we're going to learn what happens if it isn't, okay? And this is, you might say, why didn't you, this is so much easier, why didn't you show us this instead of Laplace transforms? I've had three problems with this. One, we're guessing. I mean, we're not really guessing, but we are making an educated guess as to what our answer was, and that always bothered me in math. It was like, well, you can guess what the answer is and then prove that we got the right answer. Like, you don't know what the answer is, how are you supposed to guess it? But, there we go. Second thing is Laplace transforms are, most students find them rather intimidating, especially at the end of a DE class, which is why I put them in the middle, because they're not as intimidating. And you have some time to learn them. So that's the reason why, mostly. And then you're going to see why in the when we get to it, when the right-hand side isn't 0, we're going to have to make a couple of guesses that, some of those guesses are a little involved. And quite honestly, at some point, it's like if your right-hand side looks like an e to the t cosine t here, you can guess an e to the t sine t plus e to the t cosine t and kind of get the right answer. But there's a lot of other stuff that's going on, okay, when you have to make a guess for an answer like this. So sometimes it is easier to, like, I don't remember that big table with all the guesses we're supposed to make. Can I just use Laplace transform? Yeah, we can. So there's a couple of reasons why I do it and the direction I do it in. Okay, let's go with one other complication here. Okay, so this was all of this business. Yes, there is the business that we have next. Okay, so this one I'm gonna get the numbers to be a little bit nicer. Okay, so we'll actually use some numbers. But what if we have like a y double prime plus y is equal to 0, and what if I set something like y of 0 is equal to 1 and y prime of 0 is equal to 1? Okay, you could put 2 and 1 or 3 and 1, 1 and 3, whatever you want. Okay, but I would prefer to make the numbers easy, so we just choose 1 and 1. And when we go through and do our Laplace transform, okay, so we're going to have our s squared y of s minus s f of 0 minus f prime of 0. There we go, f y prime of 0. Okay, plus y of s is equal to 0. Let's group our y of s together. So we're going to have y of s, and then what do we got next to it? It's going to be s squared plus 1. Okay, minus s minus 1 is equal to 0, because this was 1, this was 1. So what are we going to have? We have y s is equal to s plus 1 over s squared plus 1. And if you remember what we're supposed to do here, right, we're going to have y of s is equal to s over s squared plus 1 over s squared plus 1. Okay, and going back and consulting our table here with whatever's going on with this. Give me one moment. Bring up our table. All right, there we go. So if I have an s squared plus 1, s squared plus a squared on the bottom, right, we get a cosine t plus a sine t with just the a here. Okay, so we're going to have our cosine plus sine. Okay, so y of s is equal to cosine t plus sine t. Okay, and the coefficients at the beginning here were both 1s because that's how I kind of set it up. Okay, if we made them other things, then this would be different pieces here. Okay, well, what would this look like? With the new method that we're doing, what would this look like? Right, so we would have y double prime plus y is equal to 0, right? And we would guess, we would say, well, we're going to say y is equal to e to the rt, because, right, it's a differential equation, second order, constant coefficients. This should work. Y prime is equal to r e to the rt. Y double prime is equal to r squared e to the rt. So let's go through and do this. So this is r squared e to the rt plus e to the rt is equal to 0. E to the RT's were common, so we can factor those out, and then we have an r squared plus 1, right, is equal to 0. Again, e to the RT is never equal to 0. Okay, so we just have r squared plus 1 is equal to 0. R squared, just follow it through, right, equals negative 1. Now r is equal to plus or minus I. So our answer here, right, is y is equal to e to the it plus e to the negative it. Okay. I'm going to go ahead and put a C1 and a C2 here because that's what we had in our previous one, since we didn't know what our initial conditions were. So we would have to use our initial conditions to solve for C1 and C2. Okay. So there we are with that. Now I'm going to pull a little bit of other algebra with us, and what I'm going to do is I'm going to say, well, I'm going to make an A and a B such that they equal C1 and A minus B such that they equal C2. Okay, so how are you going to do that? You wait. I have two equations, right? I have two equations and two unknowns. We can solve this for any value. So if I know what my C's are, we could come up with an A and a B that would give us a consistent system to get a C1 and a C2. So you pick any numbers you want for C1 and C2, we can get an A and a B that's going to work. Now, sometimes, like if you pick C2 to be 0, like that's okay, all right? Then A is just going to be C1, and that's going to be the end of it. So yeah, we can go through and get different, whatever values we pick for this. We have two equations, two unknowns. We can solve this for any A and a B that we're going to work here. Okay. Actually, I was going to be a little bit more clever about it and say that this was going to be 1/2 and 1/2. So why are you doing the 1/2? Well, back when we first did Laplace Transform, and we had to do like a sine, so Laplace Transform of sine of t, I pulled this out on you and I said, remember that sinh of t was equal to e to the t minus e to the negative t all over 2. And then we drew an analogy to sine t, and we said this was e to the it minus e to the negative it all over 2. It's 2I. Okay, and the same thing going on here, where we had cosine of t was equal to e to the it plus e to the negative it over 2. Yeah, that's why I pulled the 1/2 here, so that we can say this was 1, right, this is C1, this is 1/2 A, okay, e to the it plus 1/2 B, e to the it, and this was 1/2 A e to the negative it minus 1/2 B e to the negative it. And what we did now is we said, well, this is 1/2 A, right, e to the it plus e to the negative it. That's this or adding them up vertically. And then we had a 1/2 B, right, 1/2 B, and this was e to the it minus e to the negative it, and this is just going to be a cosine t, and this is going to be b sine t. Okay, so that's how we're pulling that apart here. Okay, so that's what's going to happen when you have a complex um, R. Is you're going to have an A cosine t and a B sine t. Okay, so my answer to this would be, well, y double prime plus y is equal to 0. My solution after doing all of this, and this is, I'm sorry, this is something you're just going to have to once you've gone through the derivation once, we generally just know that the guess for this is that we have a C1 cosine t plus a C2 cosine or sine t. All right, that's pretty much how we do that. All right. So yeah, that's and notice it was just I. So if I had a 2i, right, we'd have a 2 in here. Okay, plus or minus 2i, we'd have a 2i here. 2t. Right. So we'll definitely do some more examples with this, but I want you to realize that the complex roots are going to yield for us a sine and a cosine. This is one of the ways you could do it. I think we could go ahead and do like a e to the RT and do a Taylor series on this and show that that's going to be our sine and our cosine. Okay, so that's another way to go is to look at this through Taylor series, right? It's yeah. All right, I think I'm going to stop here with doing this so I can pull some more examples or some more worked examples of differential equations with constant coefficients, and we'll see where that takes us. Okay, so that's the beginning of our next chapter. It's at least the intro part is a lot easier than the previous one, so there's that going for us. All right, I'm gonna let you go with that, and I will put more videos up in future.